Hello everybody, I'm very happy to host Noam. Noam Razin is a PhD student in the School of Computer Science at Tel Aviv University, advised by Nadav Cohen. His research interests include the theoretical foundation and application of machine learning. And today he will give us a talk about the implicit regularization in Tensor Factorization. So Noam, the stage is yours.
Thank you. Okay, so first off, thanks for hosting me. Very excited to give this talk here, especially because it's in person, so please feel free to ask questions. What I'll be presenting today is based off of recent joint work with Asaf Mammon and Nadav Cohen, our supervisor at Tel Aviv University. And as you can see from the title, the main focus of the talk will be the implicit regularization in Tensor Factorization. And we're also going to see how this relates to generalization in deep learning. So I'll start by setting the stage, and perhaps the place to start from is that classically generalization is often understood through the bias variance trade-off, where if you want our model to generalize, we need it to have enough capacity to fit the data, but not too much so it will not overfit. And this trade-off is often controlled by either limiting the model size, so if we're talking about neural networks, using a network that is smaller with fewer parameters, or adding some regularization term. For example, the L2 norm of the weights. So instead of minimizing just the empirical loss, we minimize the loss plus that other term, and that way we can control the capacity of our model. The situation in deep learning today, however, is quite different, where the networks we train in practice are typically over-parameterized. The number of learned weights is far greater than the number of training examples, and we can even train these networks with little or no regularization. In which case, we know that there exist many possible solutions. Okay, each solution is a weight setting for the network that exactly fit the training data. The solution, it induces a predictor, a function from input to output. So perhaps the first surprise here is that variance of gradient descent usually find one of these solutions, okay? But this is more a matter of optimization, and we will not discuss this in this one. What we will focus on is perhaps the even bigger mystery, that with natural data over typical problems, the solution found often generalizes as well. And this is in contrast to what we might have expected from classical statistical learning theory. The conventional wisdom around this is that the optimization algorithm we use, here specifically it's gradient-based optimization, induces some form of an implicit regularization, according to which gradient descent doesn't just fit the data with an arbitrary predictor, but rather with one which is simple in a certain sense. It has low complexity for some notion of complexity which we can't quite pinpoint it. And the reason that this leads to generalization for natural data, while on other types of data such as random it does not, is that we can fit natural data with predictors of relatively low complexity. So central goal in the theory of deep learning is to mathematically understand this effect. And currently a major challenge towards doing so is that we lack definitions for predictor complexity that are both quantitative, and by that I mean that we can derive generalization bounds based on them. These are typically of the form that with such and such probability, we can guarantee that the test error is upper bounded by the training error, and some term that decreases with the complexity. At the same time, we also need this complexity measure to capture the essence of natural data. And by that I mean that we need to be able to fit natural data with a predictor of low complexity. Okay, indeed, if we have such a measure that meets both of these requirements, when we fit the data, this low complexity, then we will have good guarantees for generalization, right? Because both of these terms will be low. We'll have low training error and low complexity. And as you might have noticed, this means that if we manage to fit random data, okay, get a predictor with low training error, then necessarily the complexity must be high, because we can't get any guarantees for random data. So we don't have these complexity measures yet. And just to give an example, if we consider a perhaps most commonly studied one, which is the norms of the parameter, or alternatively, the margin of the function, then in terms of the first requirement, then yes, it is quantitative. We can derive generalization bounds based on the norm of the parameters. There are many works that do so. They typically differ in the type of norms that they consider and in their dependence on the architecture. Usually it's the depth and the width of the network. However, when we look at the second requirement, it doesn't seem that it captured the essence of natural data. And in the sense, what I mean by that is, as discussed in several works, if you take just standard architectures and datasets, for example, you train a ResNet on MNIST or CFAR, then typically the norm that we get is not low enough. And this leads existing bounds to be either uninformative or even vacuous. Okay, we can get bounds with the probability of error that are greater than 1. So it doesn't tell us much. And just to be clear here, I'm not disqualifying norms or existing measures for giving us an explanation, but rather saying that currently they don't quite cut it. And therefore, the theoretical focus is often on simpler settings in which we do have an apparent notion of complexity. And one of the standard testbeds for studying implicit regularization in deep learning is matrix completion. In this setting, we're given a subset of entries from some unknown matrix, and our task is to predict the missing entries. The natural notion of complexity here is the rank of the matrix. Okay, and indeed, we can verify that it meets both of the requirements I mentioned. We can derive generalization bounds based on the rank, for example, by simple parameter counting arguments. And data, real-world data of matrix completion, such as in recommender systems, is often low rank. Okay, the matrix we try to complete has low rank. An alternative way to look at matrix completion is as a prediction problem over two input variables. One corresponds to the row index, and the other to the column index. Okay, through this viewpoint, the value of an entry ij in the matrix is just a label of an input ij. Okay, the inputs are a pair of indices. The observed entries are our training data. The unobserved entries is the test data. And lastly, a matrix is just a predictor. Okay, it's a lookup table. For each input, ij, at the corresponding location, it contains its prediction. Okay, this is just another way to look at it. Now, in this setting, what can be called a deep learning approach, perhaps, is matrix factorization, where we parameterize the solution as a product of matrices and then fit the observations using gradient descent. The objective here is of the following form, where we have a sum over observed entries. And for each one, there is some predetermined loss function. It can be the L2, L1 loss. And it measures the discrepancy between the observed value, Yij, and the value of our solution at that location. And the reason that we're interested in this setting here is that matrix factorization, this corresponds to solving matrix completion using a linear neural network, which is just a fully connected network with no nonlinearities, or put differently, a product of matrices. And while this model is trivial in terms of its expressive power, it can only express linear functions, its optimization and generalization behavior under gradient descent is highly non-trivial, and therefore it is commonly studied. You can also notice here that I don't have any explicit regularization. Okay? In particular, the hidden dimensions between the matrices, they're not limited. Okay? So the rank of our solution is not constrained, and we can express any matrix. And in matrix completion, we have an infinitely many possible solutions, right? We can essentially complete these entries in any way that we would like. So what determines which type of solution we get is exactly the implicit bias of gradient descent. An empirical phenomenon was observed a few years back is that if the ground truth matrix is of low rank, then matrix factorization, starting with from a small initialization and with a small step size, will accurately recover it. And this observation has led to a lot of recent interest into the implicit regularization at play. Initially in the same work, it was also conjectured that gradient descent converges to the minimal nuclear norm solution. The nuclear norm, it's the sum of the singular values. However, subsequent works showed that this might not be the case and instead established some form of an implicit low rank bias. Specifically, in a previous work, we showed that there exist settings in which gradient descent drives all norms towards infinity in favor of minimizing rank. And also several works show an incremental rank learning process where the rank of the matrix increases in stages and we converge to low rank solutions.
Sorry, the results are about SGD or GD?
So these results, they are mostly about GD with infinitesimally small learning rate, so gradient slow. Yeah, I think all of these results are for gradient slow. And this is also what we're going to see here. I'll get to it soon.
And is there really a difference between using SGD and GD in practice? Do people know?
So in practice, no. We see this in many, many scenarios. GD, SGD, and different types of optimizers, but the analysis is done often in gradient slow, at least for these results. Yes. And actually, we're also working on trying to see if we can convert such results to gradient descent. It's work in progress in the lab. Okay, so the whole point here is that even though this is still a very active area of research, we have a relatively good understanding of generalization. Okay, we have a complexity measure. This is the rank of the matrix. for which we both have an implicit regularization towards low complexity, and the data itself has low complexity. We can fit it with low complexity. These two properties together lead to generalization. The hope is that we can get such a full understanding, or relatively full understanding, in more advanced settings, closer to practical neural networks. And indeed, even though matrix factorization is interesting on its own behalf, as a surrogate for deep learning it is rather limited. And first and foremost, it's because it corresponds to linear networks. So it misses out the crucial aspect of nonlinearity, which is pretty much the cornerstone of modern neural networks. The second thing is that if you recall the correspondence between matrix completion and a prediction problem, then it only captures a prediction problem with two input variables. And we would like to go beyond that as well. What we're going to see next is that actually by studying tensor factorization, we would be able to account for both of these limitations in a certain sense. We would be able to study a model that does incorporate some form of nonlinearity, and also the setting itself will be able to capture prediction problems over an arbitrary amount of input variables. Okay, so are there any questions about the setup thus far? Okay, so I hope everything is clear. And now we're going to move on to tensor factorization, which is the main focus of the talk. So a tensor, for the sake of this talk, is just an n-dimensional array, a multi-dimensional array. A vector is an order 1 tensor, a matrix is an order 2 tensor, and here we will be interested in order 3 and above. And before we examine tensor completion, we can now look at a straightforward extension to tensor completion. We're given a set of unobserved entries, now it's from some unknown tensor. We're given a set of observed entries, and our goal is to predict the missing entries. And just as before, as we could examine matrix completion as a prediction problem, here we can also view tensor completion as a prediction problem. But now instead of over 2 input variables, it's over n input variables. Okay, the number of input variables matches the number of axes. Okay, here's an order 3 tensor, so it will correspond to a prediction problem with 3 input variables. Through this viewpoint, just as we had before, the value of an entry I1 to IN in the tensor, okay, now that we have tupled indices, is just the label of an input, I1 to IN. Again, the observed entries are the training data, the unobserved entries, the test data, and a tensor is a predictor. It's a lookup table, which for each input at the corresponding location contains the prediction. Now, the nice thing here that this also goes the other way around. We can look at just standard prediction problems as tensor completion tests. And to better illustrate this, consider the following super simple image classification problem, where each image has only 3 input pixels for the sake of illustration. As you can see on the right here, the corresponding tensor completion problem is of order 3. Okay? The number of axes matches the number of input variables. And the dimension of each axis corresponds to the number of different values that each one of these variables can take. Here it's 5 different values for 5 grayscale values. Okay? Each image, such as the one here, it is associated with a location in the tensor. The value of the first input variable, that determines the index in the first axis. And similarly, the second and third. At that location, the tensor holds the prediction for that input. Okay? In a standard supervised prediction task, we get multiple training samples. As you can see, these are just observed entries. And our task is to predict the label for new test samples, which are just unobserved entries. So as you can see, there's a certain equivalence between tensor completion and just standard prediction tests. Here it's illustrated for 3 input pixels, but obviously this extends to an arbitrary amount. For example, MNIST. So MNIST, we have 784 binary pixels. So the corresponding tensor will have order 784, and each dimension will be 2. So it will be a 2 by 2 by 2, 784 times tensor. Each one of the locations in the tensor is an image. Okay? You take an MNIST image, according to the values of the pixels, you can go to the corresponding location, and there's the label. Okay? Any questions about this?
Yes. But here, the amount of, I don't know, even memory to store this tensor would go exponentially with the number of variables, right? So you're essentially limiting yourself to have, like, I don't know, relatively small number of variables, or?
So that's a good point. We obviously can't store this whole tensor for standard problems, such as MNIST. It's 2 to the power of 784. We can't store it. That's why we can factorize the tensor. This is what we'll see next. And you only need to store some compressed form of it. So you never really have to compute the whole tensor. And that's where you don't run into this problem. Good question.
I think there's something misleading about it. It's not equivalent to the prediction task, because really in images, of course, every thing is continuous. It's not really discrete. There's a discretization here that can be enforced, which, I think there's an analogy that can be made, but it's not. I don't think there's a one-to-one mapping between the image classification problem from Rn to plus or minus 1 and tensor factorization.
Yeah, so thanks, that's a very good point. So there's two ways to look at it. First, in reality, we always discretize. So we have only 256 values for each pixel. So in reality, this is what is done, really. But usually, also some analysis, maybe even most analysis, do use the continuous form of pixel. So this is one limitation of the small base. This correspondence is for discrete prediction tasks, and it's a question how much is it faithful to what we have in practice. But
so the geometry of the input space.
Exactly.
You can subtract two vectors, add. That doesn't actually map easily to what's going on in the tensors. So the difference between two images, I don't know exactly.
Yeah.
Or if you had convolution, of what is the convolution in this tensor way to look at.
Yeah, so that's a good point. I will not touch upon it too much. There's also, I think, non-discrete variants to this. You can define the axes to get indices which are continuous values. You don't have to have only discrete inputs. You can have here just a continuum. But I will not touch upon it at all. So, thanks. Any more questions? Okay. Some more motivation. So now, moving on, just as we are able to factorize matrices, we can also factorize tensors. And tensor factorization, that refers to parameterizing the solution as a sum of outer products. Each outer product is called a component, and fitting the observation using gradient descent. So the loss here looks similar to what we had before, is again a sum over all observed entries. For each one we have some loss that measures the discrepancy between the observed value and the value of our solution. Okay? This is our solution, a sum of outer products. An important definition that we're going to need now is the tensor rank. The standard tensor rank that we consider is the minimal number of components, okay, the minimal number of outer products, that is required to express our tensor. So for a given tensor, if we look at the equation here, this is exactly the minimal R that is required for our parameterization to express the tensor. Okay, so specifically you can control the rank of our solution by limiting R, restricting its size. However, since we're interested in the implicit regularization here, we consider the setting where it is allowed to be arbitrarily large. Okay, so we can express any tensor, and what determines which one we get is exactly the implicit bias at play. So what does tensor factorization have to do with deep learning? Well, while matrix factorization corresponds to linear networks, as it turns out, tensor factorization corresponds to solving tensor completion using a certain nonlinear neural network. It is a specific kind of network. It has two layers and multiplicative nonlinearity. So while it is still not quite what we have in practice today, it does take us a step forward from the commonly studied linear networks. And this equivalence between tensor factorization and these type of networks is not new, and the idea actually originated around 5 or 6 years ago here at the Amnon Shashua's lab, but then it was mostly studied in the context of expressive parallel. Yeah, I'm not going to go into the full details of this equivalence. If you're interested in the paper or in the previous ones, but this is some sort of a two-layer convolutional network where the nonlinearity is from multiplication. Okay, so still not quite value, but it does take us a step forward. And with this setup in place, the question that we're interested in is when running gradient descent over tensor factorization, which solution do we get? Okay, or put differently, if we denote by WE the n tensor, this is the tensor that our parameterization creates, we would like to characterize which types of tensors does gradient descent converge to, whether they have low complexity for some notion of complexity. And an empirical phenomenon that we observed in the previous work is that, similar to what we have with matrices again, if the ground truth tensor is of low tensor rank, then tensor factorization with a small initialization and step size will accurately recover. And as part of this talk, I'm going to theoretically support this empirical phenomenon. Specifically, we're going to see that through a dynamical analysis, that gradient descent, starting from a small initialization and step size, leads to an incremental tensor rank learning process where the components are learned one after the other, and this creates a bias towards low tensor rank solutions. And then also we're going to use this dynamical characterization to show a certain tensor rank minimization result under technical conditions. Okay, so are there any questions about the setup thus far before we move to the results and analysis? Okay, great, so moving on. First, a word about the technical setting, which we already talked about a bit, that we study gradient flow, which is a continuous version of gradient descent. This is what you get when you take the learning it towards 0, and then instead of the parameters following a discrete process, they follow a continuous curve. Okay? And this curve is governed by that differential equation, so very similar to gradient descent, just that now the derivative with respect to the optimization time is minus the gradient at that location. Instead of taking a discrete step, it's a continuous optimization. And this is commonly done, and the main reason to do so is that this often simplifies the analysis quite a bit and allows to use tools from differential equations, and at the same time, the predictions made using gradient flow often closely match what we get from gradient descent in practice, at least for tensor factorization. And this is also what we're going to see in this talk. We're going to see a theory based on gradient flow, and then through experiments using gradient descent, we're going to see that the predictions made by gradient flow, they faithfully match what we have in practice. Okay? So we conducted a dynamical analysis of the trajectories that gradient flow takes, and this is the main characterization. We showed that when we start near 0, the norms of the factorization, okay, the norms of the components, each one of the components, they evolve at a rate that is proportional to themselves to the power of 2 minus 2 over n, where n is the order of the tensor. And recall that since, in our case, n is greater or equal to 3, then the exponent, that is greater than 1. Okay, and this has a profound impact on the dynamics. It means that the components are subject to a momentum-like effect, where they move slower when small and faster when large. And since we start near 0, okay, the initialization is small, then at the beginning they will be really, really small. They will barely move until each time one of them reaches some threshold and quickly rise while the rest stay small. Then perhaps another one will reach some threshold, will rise while the rest still stay at 0. So we expect this dynamics to lead to an incremental growth of components, which leads to solutions with many large components and a few small ones, which is exactly low tensor rank solutions, okay, because we can express them with only a few components.
Okay, again, how this theorem depends on R?
On
the
R?
R's component, yeah.
So each R, this theorem is true for each R. So the dynamics, the derivative with respect to time of the norm of a component, okay, this is for any R,
yeah,
it is proportional to the norm of itself to the power of 2 minus 2 over n. Okay, so this holds for any R. And we will now see how this pans out in practice and also what result we can show using this characterization. Okay, but the motivation is that when this will be small, if we have a component with a small norm, it will barely move. But when this is large, then this will also be large, so it will move faster. This creates this momentum-like effect. And it's worthwhile mentioning that this generalizes an existing characterization for matrices in a sense, but there it's the singular values that obey a similar dynamics. Okay, so they're similar in spirit, there's a similar result for matrices, but there's the singular value, so it's not quite the same. So are there any questions about the result of that?
The part in green is simplifying in some way, which we started.
Yeah.
Low rank means that some of them are 0. And nothing here is really 0.
Exactly. So everything here is going to be approximate. So we don't get exactly low rank, we get that it is very close to low rank. Yeah.
So what does that mean? Just to go back to the basic effect. Do you really get low rank, or do you get approximately low rank?
So it's approximately low rank. We are going to see next the result that we can get asymptotically as you take the initialization set for 0 exactly. But the point here is that you can just, if it's approximately low rank, you can replace it with the low rank approximation. You can just throw away all the near 0 components and you'll get basically the same solution. It will be basically the same. The values of the tensor won't change by much. Okay?
In that sense, even the random initialization is low rank. Huh?
That depends if you take a scaling invariant. If you normalize by the norm, then no, it will be of high rank. So it depends. You need to scale it. Yes.
So here
it'll be low rank because you'll have many high components. So if you
somehow you have to divide by the maximum.
Exactly. So if you divide by the norm, then these will be still large, and all the others will be.
How do you depend on the initialization being small? I mean, this is like exponentially close to zero, or in a polynomial?
Yeah, so this is just a dynamical characterization. Now we're soon going to see a result, but it will be more asymptotic. Yes, and we're going to see next in a couple of slides. It won't be clear, but it's going to be a dependence that's like exponentially small in the times that we want it to be low rank. Something. So there any questions about the result interpretation? So we can now move on to a technical problems. Okay, and I guess I'll just do it from here. So we're going to go through a brief proof sketch just to get some intuition. And this won't matter for the rest of the talk, but there's nothing too technical here, so it shouldn't be a problem to follow. And perhaps the first observation to make is that the difference between the squared norms, or each of the vectors in the component, okay, you have two vectors in the component, the difference between their squared norm is constant through time. So grain flow doesn't just travel arbitrarily through space, but rather it obeys some conservation law. Okay, this is one of them. This is constant through optimization. And what this means is that since we start off small, each one of these squared vector norms is approximately 0, and therefore they will be approximately equal to each other at initialization. And then each of them is also approximately equal to the norm of the component to the power of 2 over n. And this is due to the fact that the norm of an outer product is just the product of the norms. Okay, this is a straightforward identity, so there's nothing much in that transition. And we're now going to need just a few notations. Of course, recall our n tensor. This is WE. The loss with respect to the n tensor we denote by calligraphic L, and by hat we denote the normalized parameter vectors. Okay, and with this notation in hand, we can differentiate the norm of the component with respect to time. And what we get is that expression on the right. We have some projection term in gray, which you can safely ignore for now, and a product of n minus 1 squared vector norms. We just saw a few lines above that each of these squared vector norms is approximately the norm of the component to the power of something. So plugging this in, we get our result. We have the derivative with respect to time is approximately equal to the norm of the component itself to the power of 2 minus 2 over n multiplied by some term. And I'm obviously sweeping some details here under the rug of this approximate sign. In a sense, if there is an equality here, there's also an equality here. If it's approximately equal, then we have upper and lower bounds that converge to this as this converges to equal. Okay? And you can now see how these dynamics pan out in practice with experiments. So this is just one representative example where this is a tensor completion problem. The ground truth tensor is of rank 5 and order 4. We use a tensor factorization with 1,000 components. Okay, and fit the observations using gradient descent. And this is what we get. Each of these plots corresponds to a different experiment. They differ in their initialization scale. On the left, it's the largest. On the right, it's the smallest. And as we can see, these plots show the component norms with respect to iterations of gradient descent. Initially, they're all small. They barely move until each time one of them will quickly rise and the rest stay small. While for the larger initialization, you see that sometimes a few components rise together, and there are more components than 5 that are non-zero. As we decrease the initialization, then fewer components depart from 0. The transitions, they become sharper. Okay? When one rises, the rest don't move at all. And for the smallest initialization, you can see that only 5 components. Okay? Recall we have 1,000 components here. Only 5 are non-zero, and this is exactly the rank of the ground truth. So there is no surprise that we have exact reconstruction, like pretty much. And this is only from a fraction of the observed entries from the tensor. Okay? And from the experiments and the dynamical characterization that we saw, you can see that we have gradient descent leads to an incremental learning of the components, which leads to low rank solutions, or approximately low rank solutions. So are there any questions about this dynamic?
Yeah, if you would train it one by one, meaning first you would train the first component and then the second component, given that you have the first component, will give you the same results? Or?
So it's interesting, we haven't tried it. It should give you, I'm not sure if it will be exactly the same result, but in a sense you're supposed to get the same thing because that's what's happening here. They barely move here, so if you freeze them, it won't matter much. But we haven't tried it, so I don't know for sure. Okay, any more questions? Okay, so now we're going to see how we can use this dynamical characterization to show under technical conditions certain tensor rank minimization result. And here, for technical reasons, we focus on the Uber loss, which is often used to mitigate the impact of outliers. It is equal to the L2 loss around 0. Here it's from -1 to 1 in the plot. It's equal to the L2 loss. And away from 0, it's equal to the L1 loss. Okay? And we also need that no observation in the tensor is exactly 0. This is just for technical reasons. We will also assume that there is a leading component at initialization in the sense that it has a positive projection onto the gradient, or minus the gradient at the origin, and its norm is greater than others. What you can have in mind, what this assumption means, is that we have a component which is in a place that is better suited to rise up first. Okay, this will be the component that will first rise, while the rest will stay near 0. And under these assumptions, what we can show that if initialization is sufficiently small, then our n tensor will be approximately rank 1 for longer and longer, for an arbitrary amount of time or distance. More precisely, for any given time t, distance from the origin d, and approximation or epsilon, if initialization is sufficiently small, our n tensor will be within epsilon distance to a rank 1 trajectory, till that time t, or norm of d, where a rank 1 trajectory is just gradient flow over a tensor factorization with a single component. Okay, so it's a trajectory of rank 1 tensors. And this result essentially characterizes the first stage that we saw in the dynamics before. It shows that as we take asymptotically the initialization near 0, only one component will rise, the rest will stay near 0 for longer and longer and longer. And as a corollary, if these rank 1 trajectories converge to some W star, for example, imagine that our tensor completion problem has a rank 1 solution. Okay? And these trajectories converge to it. Then as we take our initialization towards 0, our n tensor will also converge to it. So even though we can complete the tensor with arbitrarily high rank, as we take initialization towards 0, we will converge to the rank 1 solution. Now, here, as you can see, this characterizes the first stage. So a more general characterization of the later stages was a bit out of hand for now, but this is an interesting for the future. So, any questions?
So you're assuming one of the components is has positive projection, or this doesn't happen with like high probability?
This happens like with, yeah, you have the probability that one of the components will have positive projection is with high probability. It's not, these assumptions are not very, they are a bit mild.
You can write the theorem as with high probability this happens and just assume that universal.
So I think so, but we didn't do it, and there's things that you need to verify. Here we need that the norm is greater than others by some constant factor, so there's things that you need to verify, and perhaps there's another condition, perhaps another mild condition that you need for this to hold with high probability. But in a sense, this is something that is always happens in practice. So yeah, so we should probably do it. Any more questions? Okay, so we have time, so I'll now go over also a brief proof sketch of this result to get some intuition of where does it come from. Again, it won't matter for the rest of the talk. Here we will denote the scale of the initialization by alpha. We fix some initial parameters and multiply them by alpha, and this allows us to control the scale to decrease it or to increase. And perhaps the most important observation to make here is that from the dynamical characterization from before, and the fact that under the Uber loss, the gradient is constant around the origin, because this is where we need the Uber loss assumption. And we believe it's not necessary, but it's for technical reasons, we needed it. We can show that there exists a time at which one component will be large, it will be of constant scale, it grows up, while all the rest are near 0. There will be O of alpha to the power of n. their size will still depend on the initialization state. What this means is that when we take alpha towards 0, okay, then at that time our n tensor will be arbitrarily close to a rank 1 tensor, right? Because one component will be large, will be constant size, and the rest will be pushed towards 0. And this basically completes the proof. All that's left is to note that since the loss is locally smooth, then this means that it will stay close to that rank 1 trajectory until the given time or distance. Okay?
Why did you need it to behave like L1, the loss far from the origin?
So that's a good question. It's a technical reason. We need to ensure that one component will rise and will not stop rising at some stage. And here, since it's constant around the origin, then we can show that that inner product that we saw before from the character. Anyway, we can show that it continues to rise and doesn't stop. In practice, it happens for pretty much any loss we try. L2, L1, even classification losses like binary constant entropy. But we had a tough time showing it, so this is a technical assumption. But we do not believe that it is necessary. It seems true regardless. Okay. After these technical details and result, let's switch gears a bit and go to a more high-level view of the matter. And let's go back to the challenge in understanding the implicit regularization in deep learning. And that's that we lack complexity measures that capture the essence of natural data. And let's recall what we saw. We have tensor completion. That corresponds to a multi-dimensional prediction problem. We have tensor factorization, which corresponds to solving that prediction problem using a certain specific kind of non-linear neural network. And the implicit regularization of that network is towards predictors, towards tensors of low tensor rank. Seeing this, the question we ask is it possible that tensor rank can serve as a measure of complexity for predictors? Okay, can we fit natural data with low tensor rank? And to check whether it might, we run experiments. We try to fit standard data sets with predictors of low tensor rank. Specifically, what we are going to see now, we consider MNIST and fashion MNIST, where for simplicity, we convert them to one versus all binary prediction tasks, and we fit the labels using the L2 loss. Just to be clear about what's going on here, okay? Recall that each one of these prediction tasks, it's a binary, we have binary images, it's a prediction task over binary images, so we can look at it as a tensor completion problem. The tensor completion problem will be of order 784 because there are 784 pixels, and the dimension in each axis will be 2. And then we can fit these data sets with tensor factorization where we explicitly control the rank now. Okay, we start from rank 1 and so forth, and we would like to see whether we can fit them with low rank. And we compare each of these data sets to 2 randomized variants. In the first, we randomize the images, and we replace them with noise. In the second, we randomize the labels. We permute the labels and keep the images as they are. And this is what we get. On the left, that's MNIST. On the right, fashion MNIST. In blue, it's the original data. Red and purple, that's the randomized variants. Each marker here is a different experiment. Okay, it corresponds to we fit the data with a predictor, a tensor factorization of this tensor rank, and it reports the error that we get. We have here both training error, okay, and test error in the semi-transparent one. And what's important to see is that with predictors of low tensor rank, the original data is fit far more accurately than the random variants. And already with tensor rank as low as 1, we get a relatively good fit for the original data, where for the randomized variants, it's no better than random guessing, okay? So we can't really fit them with tensor rank 1. Well, the original data we can fit relatively well. And you can see that tensor rank captures not only the implicit regularization of some non-linear neural network, but it also seems to capture at least some aspects of natural data, at least for MNIST and fashion MNIST. And seeing this, we believe that perhaps tensor rank may shed light on both the implicit regularization neural networks and the properties of real world data that translate it to generalization. So are there any questions about the experiments and the conclusions?
So, can you translate this complexity to neural network language? I mean, what does this mean on the neural network that fits the data?
Yeah, so the tensor rank here is of the function. So here specifically, it's indeed over discrete inputs, so this is a certain limitation when you're looking at it now, but you can train a network, okay, and then you can just predict its outputs on the data, and you can check what's the rank of its predictions. Okay, it's a measure over the function. It doesn't depend on the parameterization. As long as the function is from a discrete input space to some continuous space, we're now trying to work. You can extend this to also not discrete problems. But this is more a going forward hypothesis, right? This is not something we can say for sure.
But the hypothesis is that when you're training neural networks on natural data, the function that you get has low tensor rank.
Yes, we're saying that perhaps tensor rank might be a complexity measure that is low or implicitly minimized. This is something that we're trying to figure out and check.
So in this experiment, you trained a regular neural network and measured its tensor rank afterwards, or you trained a tensor factorization?
Oh, so here is tensor factorization. Now, it's a good question because when you train a network, there's very many nuances here, because if you fit the data well and get good generalization, then essentially the fact that the data can be fit with low rank is the same as the network learning function of low rank. It's the same because it learns pretty much if you get 99 accuracy or 95 accuracy, then if you fit the data with low rank, it's the same as if you fit the predictions of the model. So there's a lot of nuances there that we're now trying to tackle. Okay, so I'll conclude. We saw that a central goal in the theory of deep learning is to understand the implicit regularization in deep learning. Yes. And a major challenge towards doing so is that we currently lack measures of complexity that capture the essence of natural data. Aiming to make progress towards this goal, we study tensor factorization, which is equivalent to solving a certain multidimensional prediction problem using a non-linear neural network, some specific kind of non-linear network. And through a dynamical analysis, we showed that the implicit regularization of this model minimizes tensor rank. Seeing this, we explored tensor rank as a measure of complexity and saw that we can fit standard datasets, at least NNIST to fashion NNIST, with predictors of low tensor rank. And indeed, as I said before, just to emphasize, going forward, we believe that perhaps tensor rank may pave the way to understanding both the implicit bias of nonlinear neural networks, so perhaps even more elaborate ones with other types of nonlinearities, and properties of real-world data that translate this implicit bias to generalization. And now one last word about ongoing work before I finish. So the tensor factorization that we now saw, that corresponds to a shallow network, a two-layer network. And the implicit bias of this model is towards minimal tensor rank. Now, a possible limitation of tensor rank as a measure of complexity that it is actually oblivious to the ordering of the inputs. Okay, if we take a tensor and we permute its axis, its tensor rank will not change. And in the viewpoint of a complexity measure, this means that if we permute the inputs, we permute the pixels of the image, then the complexity will not change. And this is obviously something that we might want to take into account. And a possible way to address this limitation is to consider hierarchical factorization, such as the one on the left. And adding hierarchy to the factorization, that actually corresponds to adding depth to the network. So first we benefit from that now the model is even another step closer towards practical networks. And the second thing is perhaps that the implicit regularization of this model is towards minimal hierarchical tensor rank, which is a generalization of the tensor rank to these hierarchical factorization. And the interesting thing about it is that it does take into account the ordering of the input. So while standard tensor rank might be a bit too simplistic when you go to more complicated settings of datasets and nonlinear networks, but perhaps this hierarchical rank might help us in understanding generalization and deep learning. And there are some positive results, still work in progress, but it seems to have some positive results about this. So are there any questions?
Yes, the audience asks, in tensor completion, is zero initialization used in practice? Shouldn't some form of truncated tensor SVD should work better?
Okay, so before I answer that, because it's not exactly related to this slide, so I'll just say, okay, first of all, thank you again for hosting, and I'll take more questions. So about that, it's a good question. So there are many tensor techniques, tensor factorization to try and train and fit data that form that tensor wall. In tensor completion problem, this is something that is studied unrelated to deep learning. Okay, And there are different types of techniques that work for different types of problems. But here we're trying to study the implicit bias under settings that are closer to what we do in deep learning. So usually we initialize near zero, and therefore we would like to understand what happens when we initialize near zero. So this is a more...
Is it better in terms of iterations, in terms of convergence? I don't know.
What one?
You suggested to do the regular tensor factorization with missing data using a lot of different matrices, right? So the question is whether this technique is better to do matrix completion than other ones.
So no, this is more of a theoretical motivation. We're not suggesting that you do this, but it does have some practical uses. What it means is that you can take a tensor factorization. Usually, people assume the rank of the gram truth is low, or they assume that it is low than some value, and then they explicitly restrict the rank by taking fewer components, or in matrices they limit the hidden dimension. And this works well in practice. And what these results show, both for matrices and tensors, that even if you don't know it and just initialize near zero, you'll be able to get an approximate low rank solution. You'll be able to realize what's the real rank of the data. So it might have some practical uses, but obviously this is way more expensive than training a smaller tensor factorization. So the interest here is more from a theoretical perspective of understanding models that are nonlinear models and studying implicit regularization. Any more questions about other things?
Thank
Okay,
you.
so
Thank you very
thank you
much.
all.